Hello, my name is Yadira Rivera and I am doing homework 2, problem number 9, that states, let A be a matrix with entries 2, 1, 3, negative 2. Find an elementary matrix E such that EA equals, and here we have 4 cases. The first one is EA equals a matrix 3, negative 2, 2, 1, a matrix, the second case, 2, 1, negative 12, 8. The third case, that EA equals negative 10, 9, 3, negative 2. And the fourth case, that EA equals negative 3, 2, 2, 1. All right. So for the first case, we have that EA equals 3, negative 2, 2, 1. Now A equals 2, 1, 3, negative 2. Simply by looking at these matrices, we can tell that there is one elementary row operation, a type 1, in which row 1 and row 2 are switched. This is an elementary row operation type 1. An elementary matrix is different from the identity matrix because in it there is one elementary row operation. So an example would be that here, this is the elementary matrix. It's the identity matrix with an elementary row operation, and it would look like this. So our answer would be that E equals a matrix 0, 1, 1, 0, which could also be written as the elementary row operation times A of row 1 interchanged with row 2. Okay, so that's basically that, and this is the answer to part A, the first case. Moving on, we have the second case in which EA is equal to a matrix where the entries are 2, 1, negative 12, and 8. And here we can tell that the first row has no changes compared to the first matrix A, but then the second row does have a change. And by looking at these, we can tell that negative 12 divided by 3 is negative 4, and 8 divided by negative 2 is negative 4 also. So the elementary row operation that happens here is a type 2, that you multiply a constant, by the row, and that is the operation that takes place. So in this case, it's negative 4 times row 2, which would be the new matrix, EA, which is entries 2, 1, negative 12, 8. Demonstrated in another form, elementary, and the elementary matrix would be the identity with this elementary row operation, which would therefore look like this: 1, 0, 0, negative 4. That would equal E. And when you check and multiply EA with the elementary matrix E, 1, 0, 0, negative 4, multiplied by A, it does indeed equal the original matrix we had stated that has entries 2, 1, negative 12, 8. Therefore, that is also written in this form: EA equals elementary row operation of negative 4, row 2, times A, which gives us this matrix. That is the second case. Moving on, we have the third case, where EA is equal to a matrix with entries negative 10, 9, 3, and negative 2. In this matrix, we see that there is no changes to the second row, However, there is a change to the first row, and it is not a change that can be obtained by multiplying by a constant. So it's easy to assume that this is a type 3 row operation where you multiply the second row by a constant and add or subtract it to the first row. By analyzing this matrix, we can see that 2, for example, if 3, we multiply it by 4, 3 times 4 is 12. So let's say 2 minus 12 would be negative 10. So then the same case would work for the second entry of the second row and the first row, that, let's say, 1 minus 4 times negative 2, which would be plus 8. 1 plus 8 would be 9. So we can see that this elementary row operation does indeed work. Is the row operation that's taking place in this equation, in this operation. And here it would be expressed, the elementary matrix would be the identity matrix with this elementary row operation, which would therefore be written as 1, negative 4, 0, 1, because 1, 0, 0, 1. Row 1 minus 4 row 2 would be 1, because 1 minus 0 is still 1. And then 0 minus 4 times row 2, which is 1, and times 4 would be negative, times the negative 4 would be negative 4. So it should be 0 minus 4 would be 4, negative 4. So therefore, this is what E equals. And then here, when we check our work, and we use this matrix that we found, E, here we have E times A does indeed equal this matrix. Let's see. We have 1 times 2 is 2, plus negative 4 times 3, that's negative 12. So it's 2 minus 12, negative 10. Here we have, for the second entry, number 9 here, would be 1 times 1 would be 1. Negative 4 times negative 2 would be 8. So 1 plus 8 would be 9, which is correct. Here we have 0 times 3 is 0. No, sorry. 0 times 2 is 0. Plus 1 times 3 would be 3. Okay. And then we have 0 times 1 is 0. Plus 1 times negative 2 would just be minus 2. So this upper elementary matrix is indeed the one necessary for EA to equal this matrix. So this case is completed. And then we have the fourth case, in which EA equals an elementary matrix negative 3, 2, 2, 1. By looking at this matrix and comparing it to the original matrix A, we can tell that the rows were switched, but that is not the only operation taking place, but also that then after being switched, this row is multiplied by a negative 1, and therefore this is what EA would be. But this cannot be an elementary matrix because there are two elementary row operations. In an elementary matrix, there's only one elementary row operation. So E is not an elementary matrix. So in order to find E, let's let E equal a matrix that you have the entry E11, E12, E21, and E22. So EA would be E times A, which would equal EA, as in this case was already stated. So let's see, E1 times E times 2 plus E12 times 3, stated here. Then we have E11 times 1 minus 2 times E12